Hi, my name is Andrew Morell, and I'm a PhD student at the Autonomous Vehicle Systems Laboratory at the University of Colorado Boulder, where I study under Dr. Hans-Peter Schaub, my co-author on this paper, which is back-substitution-based spacecraft dynamics modeling with selective configuration space branching. And I'd like to start by just going through this title line by line to look at what we're talking about today. And first of all, the what we're doing, spacecraft dynamics modeling, when we're looking to study the motion of spacecraft under the influence of different forces and torques, we usually start by looking at the overall translation and rotation of our spacecraft through space. We start doing that by looking at its central hub's position and attitude throughout time. However, as our spacecraft becomes more complex and has different what we refer to as time-varying geometries on it that are affecting the dynamics, we need to model those as well. And so, for example, here, two solar panels may have each one or more degrees of freedom, which when they rotate to achieve a better sun heading are going to impart a reaction torque on our central hub. We also commonly see some kind of momentum exchange device, such as reaction wheels, which also as they rotate are imparting a reaction torque on our central hub. And then finally, we commonly see thrusters on spacecraft exerting external forces and torques on our environment to achieve some motion of our spacecraft. Now, this spacecraft we see on the left here is what I'll from here on refer to as our classical spacecraft architecture, commonly used, well studied, versus what we see on the right here, what I'll refer to as modern spacecraft architectures, with some more ambitious components on them, which in the case of these two vehicles are seeking to achieve on-orbit servicing. So starting with the one on the top there, that's Astroscale's Life Extension in Orbit, or LEXI vehicle, which at first looks somewhat similar. We see two solar panels extending off of it. There are likely some momentum exchange devices inside. However, when we look for the thrusters on this vehicle, we no longer see them attached directly to the hub as we did before. And if we look, we actually find them way out on the ends of robotic arms. In this case, 4 of them, each 2 rotational degrees of freedom. So as these arms are rotating around to point our thrusters, they'll be imparting reaction forces and torques on our central hub. And then as those thrusters fire and exert external forces and torques, they'll no longer be in the same position in orientation with respect to our central hub throughout time as they were previously. Also on the LEXI spacecraft, we see 4 docking arms, also 2 degrees of freedom, but now with 1 rotational and 1 translational degree of freedom each. And as those are grappling onto another spacecraft, we'll also consider those to be external forces and torques applied to our hub. And then finally, in the bottom right here, we see Northrop Grumman's updated mission concept for on-orbit servicing, in which they have one larger mission robotic vehicle that we see on the left, holding onto one of its smaller mission extension pods. Now we have in our total spacecraft this secondary hub with its own position and attitude, its own solar panels that may have degrees of freedom, as well as, in this case, a multi-degree of freedom actuated robotic thruster arm. So now that we know some of the more complex dynamics that we're seeking to model from these modern architectures, another way we can think about these is topologically. So thinking about how our components are attached to our vehicle. So for the case of this classic architecture, we can see we have a couple of solar panels, a delta V thruster, some attitude control thrusters, some reaction wheels. But the important thing to observe here is that they're all attached directly to our central hub, or in other words, we'd phrase this as being attached in parallel. And we can start to think about how some of this topology might change as we move towards those more modern architectures that we saw on the last slide. So we can imagine as we have something like a robotic docking arm, we now have a end effector, which is exerting external forces and torques, but with some number of degree of freedom robotic arm between it and its central hub. And then similarly for those thruster arms that we saw on the LEXI spacecraft, these also now have some number degree of freedom robotic arm between them and the hub. And we'd phrase these kind of components as being attached in series with our central hub. Another situation that we see as we look to increase the fidelity of our spacecraft modeling, of our dynamical modeling, as we say, model drag or solar radiation pressure on our vehicle, if we want to take into account the changing orientation of, say, our solar panels, which have a large cross-sectional area, as we compute our drag and solar radiation pressure, these are now a splitting off of 2 different dynamical effects that we want to apply to one component. So that's another kind of dynamical branching that we see here. And with this modern architecture, we finally get to the how we're doing this, so that back substitution based part of our title, which before we go into too much farther, we just want to lay out some mathematical terminology so we have a common language that we're working with here when we look through the mathematics. So just to quickly point out, we have an inertially fixed frame N on the left-hand side here, and then in gray we see our central hub on our spacecraft with its own body fixed frame B. So when we're talking about the translation and rotation of our spacecraft throughout time, the states we care about are this r double dot bn linear acceleration of our hub and omega dot bn angular acceleration. Also, we see here a couple different components shown in blue. So we have a fuel tank and 2 solar panels, and each is going to have its own different parameters as far as where it's located, how it's changing in time. But what we just want to summarize here is that we'll refer in general to any component time-varying dynamical state to be this alpha or alpha double dot for the acceleration of those states. And now there's 2 main assumptions that we're making classically to use our back substitution method, which are 1, that all these bodies are rigid. So not to say that no flexing is occurring. If we take, for example, our solar panel that we see here deflecting with respect to our central hub, it's just that it's going to be purely having first order flexing about the joint between 2 rigid bodies and no deformation of the bodies themselves. And then the second assumption that we're making here is that all the components are connected directly to this central hub, in other words, in parallel, which, as we just showed on the last slide, is no longer an assumption we want to be making, so we need to back this assumption out of the back substitution method. To get a better understanding of how we're doing that, we'll take a quick look at why it's been previously important that we consider all of our components to be attached in parallel. Just starting from fundamentals with our dynamics here, this is just F equals ma, but if we expand this equation and start to populate a mass matrix and look at the associated state acceleration vector and push all of our other terms to the right-hand side, these non-acceleration terms, we see here our r double dot bn and omega dot bn in our state acceleration vector, so that's our hub's translational and rotational acceleration, and then we have just a list of however many component states here, component accelerations. And if we're to now think about those as we break out some submatrices of our mass matrix, we have our hub on hub contributions, we have our component on hub contributions. Similarly, vice versa, we have our hub on component contributions, and then in the bottom right hand corner here we can see our cross component contributions and self component contributions. And it's important to realize here that when all of our components are attached in parallel, we see this nice behavior that all cross-component contributions are going to be 0, which should be intuitive to us that if none of them are explicitly interacting with one another, they're not going to have any explicit dependencies in our equations of motion here. So that's what we have previously gained under that back substitution method assumption. And it's not to say that we can't model some of these more complex components on spacecraft using the existing back substitution method, but now knowing that we need to have no cross or explicit cross coupling between our components, the way you would have previously had to do that is by considering these to be one component each and derive a set of equations of motion that are specific to it. So one of the benefits of the back substitution method is that currently if you model a reaction wheel or a thruster or a solar panel, you can dynamically add and subtract these components to your spacecraft without having to rederive your total spacecraft equations of motion. We want to continue to be able to do that, but now with branching components. So instead of when I decide I want maybe 6 degrees of freedom instead of 7 on my robotic arm having to rederive equations of motion, for that we want to be able to just swap in these different dynamical submodules and match them up with one another. So similarly for the solar panel with solar radiation pressure and drag applied to it, say we just had one of those and we wanted to add the other, currently you'd have to rederive new equations of motion for that, and we want to be able to modularly add and subtract them. And then also in our kind of asterisk selective configuration space branching that we've made a part of this title in this work is not to say that we can do any kind of branching components here. What we're now enabling is applying components or effects that are pure forces and torques on otherwise our spacecraft onto any kind of component with its own states to be propagated through time. So this allows us to apply the forces and torques of, as we show here, thrusters or robotic end effectors, solar radiation pressure, drag to things like robotic arms or solar panels or any time varying components, but not necessarily enabling, say, adding a reaction wheel to the end of a robotic arm or stacking of components with states on one another in that way. So going back to the mathematics behind our back substitution method and looking at what we're actually changing at the mathematics level to enable this, we can start by looking at our overall translational and rotational equations of motion for our total spacecraft, which at first looks like a lot here, but we can see some familiar terms of, on the left-hand side, are r double dot bn, omega dot bn, and alpha double dot summed over all of our components. So all of our accelerations we see here on the left-hand side. And then on the right-hand side of these equations, we see our external forces and torques applied to our spacecraft and some cross-coupling terms. We can also look at the specific equations of motion for each of our component states. We see here also, again, r double dot bn and omega dot bn in this equation of motion. These are fully coupled. And then these are general. So we see in the effector equation of motion, this A, B, C prepended. This is to say this is working for any components that we're attaching. And if we look here, what's shown in red is where we are subtracting out what are previously directly applied external forces and torques on our hub and putting them in the green location. So in our effector equation of motion on the bottom there, the C term is now getting those forces and torques and then implicitly finding their way to the overall equations of motion through the alpha double dot shown in the translation and rotation. And then on the far right hand side here, we also see this vec trans and vec rotational components, which is where we're seeing those forces and torques still appear explicitly in our equations of motion. And if we take a little bit deeper look at this, we fleshed it out here and in the paper, just showing the final results here, worked for a 1 degree of freedom rotating robotic arm. So we get, for starters, summing over any forces and torques applied to this robotic arm as this S sub S and L sub S. And then we first apply them in our augmented 1 degree freedom effector equation of motion. So that C term takes on the torque here as a rotational degree of freedom. And then in our vec trans and vec rotational, we apply that force. And then in the torque case, we're also finding the torque occurring from the force applied at some distance out from the center of our spacecraft. And then finally here, showing an implementation of this 1 degree of freedom robotic arm, now with a thruster attached to the end of it, mounted at 90 degrees. We've implemented this using the Basilisk simulation framework, which leverages the back substitution method. And then augmented here, we show the deflection of our robotic arm as well as the rate of deflection. Here shown in the golden line is what we refer to as our hub excited flexing. So this is using the old method of the back substitution framework where when the forces are generated by a thruster, they're applied directly to our central hub. We see the hub accelerate and the deflection occur as the robotic arm lags behind it under some stiffness and damping that we've given it. And then in the blue line here, we show what we're referring to as our platform excited flexing, where the forces generated by the thruster are genuinely applied to that robotic arm first, which then translates them through to the hub. And we see here very clearly the main benefit in modeling the dynamics this way, and that our robotic arm deflects in the opposite direction, as instead the forces accelerate the robotic arm and it's the hub that lags behind. And not only do we get this more realistic flexing in the opposite direction, but also a larger magnitude, as the same force applied to the smaller mass and inertia of a robotic arm creates a larger deflection than otherwise accelerating a likely more massive hub. We can also look at the variation over time of our hub states and see how those are affected. Shown in the solid line here is our results from platform excited flexing, and in the dashed line are results from the hub excited flexing, where we don't see any major difference in the attitude of our spacecraft. But then when we look to the angular velocity, specifically during our transients when we turn this thruster on and off, we see a larger oscillation in that angular velocity as we have a larger deflection of our robotic arm. And we can also look at the translational states of our central hub, shown here the position on the left and translational velocity on the right, where we see a more significant variation due to the compounding effects of the rotation of our hub as well as the deflection of the robotic arm. And just over this 60-second time window, we see already somewhat significant differencing between that platform and hub excited flexing. So in conclusion here, this alteration of the back substitution method is surmounting a previous limitation where branching of components could not occur, and this also is allowing us to achieve a more accurate flexing behavior with this new platform excited flexing as opposed to hub excited flexing. And we greatly increase the number of spacecraft architectures that can be easily modeled in a back substitution framework. As we showed earlier on in the presentation, some of these more ambitious architectures coming out of companies like Astroscale and Northrop Grumman. Next steps for this would be to generalize the branching to n degree of freedom successive rotating bodies, which my colleague João Vaz Carneiro has developed using the back substitution method to have any number of successive rotating bodies in effect modeling robotic arms. And we'd like to be able to apply these force and torque dynamical effects anywhere on those rotating bodies in the same way that we did this initial proof of concept for a 1 degree of freedom rotating body. We'd also like to expand the analysis at a controls level and study the differences in resulting motion and resonance analysis if we have, for example, pulse control of a thruster on a robotic arm, as we just showed. So thank you so much for listening. Please be sure to check out the full paper for more details, and also see a link here to the Basilisk simulation framework implementation of the back substitution method, where a lot of this work is available as open source code.